Students, this is the help video for the Unit 6 Review Study Guide Part 2, 6.6 to 6.7. It says right here, draw the following quadrilateral of a translation 3 units to the left, 2 units down. So the easiest way is you could just bunny hop this. 3 units to the left, 1, 2, 3, and then 2 units down, 1, 2. Or there's a mathematical way you can do that. I'll show that to you in just a moment. So our original point here is positive 3, positive 4. That's your original point. And then 3 units to the left would be minus 3, 2 units down, minus 2, which would put us at the coordinates 0, positive 2. 0, positive 2, which is exactly where we ended up. So that is both the physical and the mechanical way of doing a translation. Says in a coordinate plane, point A is translated to point A, negative 4, 2, is translated to the point negative 2, A prime. This is before the translation. This is after the translation. Under the same translation. What it means by under the same translation, it means under the same rule. So if you just do a picture of this, right here, A is at negative 4, positive 2. Negative 4, positive 2. That's A. Negative 4, positive 2. A prime is at negative 2, 0. A prime is at negative 2, 0, which is right here. That's A prime, negative 2, comma 0. So you ask yourself, what was the motion? The motion here was 2 units to the right and 2 units down. So the motion was add 2 to the x minus 2 to the y. So we're going to add 2 to the x minus 2 to the y, add 2 to the x minus 2 to the y. And our b prime in this case is negative 1 plus 2, that's positive 1. 6 minus 2 is 4, that's going to be b prime. C prime, negative 2 plus 2 is 0, 4 minus 2 is 2. We're going to reflect across the y-axis. Here's the y-axis. To flip over the y, that's a horizontal motion. All you do is you opposite the x motion, the x coordinate. So for example, this is at negative 5, negative 2. I just opposite the x coordinate and I get 5, negative 2. This one is negative 3, negative 3. You opposite the x coordinate to flip over the y, so that's 3, negative 3. And you just keep going. This is negative 2, negative 8. We're flipping the y coordinate. And this one over here is at negative 8, negative 5, flip the y coordinate. and we get 8, -5. This one says draw a reflection across the x-axis. So to flip over, here's the x-axis, to flip over the x, that's a vertical motion, you simply opposite all the y coordinates. So whatever these y coordinates are right there, you simply opposite it. And you're going to take it this way across the x-axis. So to flip over the y, you opposite the x. To flip over the x, you opposite the y. We're going to rotate 90 degrees, in this case clockwise. It's always a good idea just to get a general impression what direction you're going. And it says right here, if we're going clockwise, we're just going to go this way in general, and we're rotating 90 degrees. I'm just going to call that A. That's going to be -2, +5. B is at -5, +4. C is at -3, -1. To rotate 90 clockwise, you switch and flip to the right. To rotate 90 clockwise. So first we switch. Now you're going to flip the sign on the right only, because it's clockwise. So we're at 5 and +2. That's A prime. 4 and +5. It's B prime, -1, +3. C prime. Now, to test to see if this actually works, you choose any 2 points. I'm going to choose the B point. Origin to B, origin to B prime, and you take a look. Yes, it is 90 degrees. Yes, we rotated clockwise. Counterclockwise, you would do switch and flip to the left. So to rotate 90 counterclockwise, you switch and flip to the left. So first we switch. And then we do counterclockwise, flip it on the left. See if it worked. You choose any 2 points. We're going to go from origin to B, origin to B prime. Yes, it's 90 degrees, and yes, the motion was counterclockwise. To change in size, you multiply. So to change in size, you multiply. We're going to dilate this by a scale of 2/3, which means we're shrinking. If your K factor or your dilation factor is bigger than 1, you're going to enlarge. If K is less than 1, you're going to reduce. And since 2/3 is less than 1, we're reducing. So you just get your points here. I'm going to call this A, and that is 9 and 12 over 9 up 12. B is over 6 up 9, and C is 12 and 9. We're going to dilate everything by 2/3, so that's called arrow in, arrow out. So I have 9 and 12, 6 and 9, 12 and 9. 2/3, 2/3, 2/3. We're multiplying everything by your dilation factor. You do arrow in, arrow out. 3 goes into 9 3 times. 3 times 2, this becomes 6. 3 goes into 12 4 times. 4 times 2, that becomes 8. 3 goes into there 2. 2 times 2, that becomes 4. 6. And when you graph these points, you should end up with a same shape, different size, because these are similar. So 6, 8. That's going to be our A prime. 4, 6. That's going to be B prime. And 8, 6. C prime. Connect, same shape, different size. It obviously has shrunk. So this one, if you were to dilate by 2, you're going to be getting larger. So for this one, you're going to use the slider. And it says right here, you're going to dilate by a factor of 4. So what that means is you take the 1 here, and whatever this shape is, for example, this shape is right here. If you dilate by 4, you're going to drag this to 4. So from 1 to 4, and that means all the side lengths are going to increase by a factor of 4. So right now we have a 1 by 2 shape, and it's going to become a 1, 2, 3, 4 by 8. 1, 2, 3, 4, 5, 6, 7, 8. And it says right here, the area of the original figure, area. That's only 2 boxes. So the area of the original is 2 square units. The area of the larger is 4 by 8 is 32 units. Make note of that. So the scale factor went from 1 to 4, but the area went from 1 to 16. This is what's going on here. In the first dimension, scale factor is the ratio of the sides only. This is like x to the first, y to the first. Area is the second dimension, so it's x squared, y squared. So if I square 1 and I square 4, you get 1 to 16. So although the side length is 4 times as big, the area is 16 times as big. The area of the final figure is 16 times larger than the original. Are they similar? Yes, same shape, different size. Lines of symmetry. We're going to do this briefly in class. Lines of symmetry are really simple. Ask yourself if I can take the shape and fold it and get the exact same image. That's a line of symmetry. Wherever you can fold it and get the exact same image. For example, it is obvious that I have one line of symmetry here. If I fold along that line, the left-right, it's the exact same image. Here, if I fold along the red line, it's also the exact same image. So in this image, there's only 2 lines of symmetry. If I fold this way, you don't get the exact same image. What is rotational symmetry? Rotational symmetry means you can rotate less than a full circle and get the same image. You can rotate less than a full circle and get the same image. For example, in a standard letter H, I could take the letter H and I can rotate only 180 degrees, and I have the same letter H. So the letter H does have rotational symmetry. The letter P, however, in order for me to get the same P, I have to go all the way around and rotate a full 360. If I do 180, the P looks like this. So H has rotational symmetry, the letter P does not. It says right here, determine if it has rotational symmetry and what's the smallest angle of rotation. So if I rotate this triangle, when you rotate, imagine it as a circle. All I would have to do is rotate from here to there, and then this would come up and you'd have the same image. So yes, it does have rotational symmetry. What is the angle of rotation here? Think of it as a circle, and it's simply 360 divided by 3, which is 120 degrees. So I only need to rotate this equilateral triangle 120 degrees to get it. So does it have? Yes, 120. Does this 4 have rotational symmetry? No, because I have to go a full 360 to get the same number of 4. Does this have rotational symmetry? No, it does not have rotational symmetry. You have to go a full 360 in order to get the same image. Does it have point symmetry? Can you rotate around a single point? The answer is no. Does this have rotational symmetry? Yes, because you only need to rotate that little bit in order to get the same sun. What is the angle? Well, imagine this as a circle. And these are all pie slices. So we have 360, and we have 1, 2, 3, 4, 5, 6, 7, 8 pie slices. So my angle of rotational symmetry is simply 45 degrees. So does it have point symmetry? Yes, 45 degrees. Circular dial has 10 evenly spaced points. Evenly spaced. 10 evenly spaced points. Which means I have 10 pie slices. So it's 360 divided by 10. So each pie slice rotates 36 degrees. So it says if point A is at the top of the dial, suppose it's turned counterclockwise until G is at the top. So coming this way, counterclockwise until G is at the top. How many degrees does the dial have to turn? That is 36 times 1, 2, 3, 4, 5, 6. 18 plus 3. It must turn 216 degrees. The hand of the clock is pointing 9 o'clock. Suppose the hand moves clockwise till it points to 2 o'clock. How many degrees does it have to move? Well, a clock has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 slices. So it's 360 divided by 12. That's 30 degrees each. So each of these pie slices are 30 degrees. 1, 2, 3, 4, 5. 5 times 30 is 150 degrees.